All right. Hello, everybody. My name is Nick Larson. Today is June 2019. It's about 12:20 in the afternoon. I would like to thank everybody for joining. I'd like to throw a shout out to Mary Page 11 for the Twitch Prime subscription while I was offline. Thank you for that. Now, let's talk about today. So, up to this point, we had been working on some decision tree stuff and we sort of reached our goal, right? We got it super fast. I'm going to eat some brownies. I love brownies. All right, we got it super fast. Then I sent it off for code review so that we could, get it ready to go to production and all that. And it turns out there was a bug. And it was only looking at one tree ever. And there were two different versions of it. The first version only looked at a single sample, and the second version looked at all the samples. And it was the one that looked at all the samples that was super fast. And it turns out that's the one that had a bug in it. But the one that I was testing for correctness was the other one. So that was a mistake. And I have since gotten that fixed. It turns out it jumped the time all the way back up to about 120 milliseconds. Maybe 110 on the benchmark. And when you divide, or I guess it was like 58 or so on the benchmark. And that, of course, was close to where we need to be, but still far from it, because getting those last few little bits of your performance are difficult. That being said, a lot has happened since then, and what I want to do today is not actually get into it. I want to write about it and start drawing some visuals to show basically all the stuff that we've learned over the last 2 weeks and see if we can produce something that we can post on dev.to or something like that. And so that's sort of the goal today. Is I don't want to get too far past working on this stuff where I start forgetting about some of the things. Is Matt, thank you so much for the follow. You are my 200th follower. I really appreciate that. That's amazing. Thank you so much. And I know you're my 200th because it just gave me a little pop-up saying that I had reached the next level of whatever it is. Okay. So a lot less code today, a lot more going over the stuff that we've done, and a lot more drawing some visualizations of why it was successful, why it wasn't successful. And then I also want to describe the stuff that the other people at my job were working on. Because we were sort of competing is not the right word. We were going independent directions, and theirs turned out to be faster under certain conditions. And then we had an idea last night that we implemented that has promise, but still has a couple of little hiccups. But it's super interesting. So first thing I want to point out is the feature space. We have tons and tons. Let's just go ahead and look at this one more time. The goal, the plan, the problem is we have Stack Overflow. Oh, and of course, I always do this. I always forget to turn my pie hole off. If you don't have a pie hole, I super recommend getting one. If you're into ad blocking, at least. It's a way to block ads via DNS, which is a lot better than going through what's in the browser and controlled by public list. It basically will not load. Alright, we're going to turn this off for an hour, and then we're going to reload this. Alright, so if we go to a page, nope, that was a bad example. That's a good example. We see jobs that show up in the sidebar, and our job is to replace the model that scores each of these jobs for the person who is visiting. We record a bunch of information about the people who are visiting. The way that we do that, if you're curious, is through An application, cookies on Stack Overflow, this thing called prov right here. Prov is a cookie that just is basically a GUID. And the first time you come to Stack Overflow, you get assigned one of these. Hey, what's up, Ryan Roberts? Good to see you, man. I hope you have found a project and whatnot. Hope you're, enjoying your summer and that as well. So we tag you with a cookie. We start recording stuff about you. The kinds of stuff that we record are like, you viewed this page and there are the tags JavaScript, Vue.js, Vue component, parent-child, things like that. And what we want to do is basically turn this into a way to show you some ads that are related to the stuff that you do. No, you've been slacking a lot, but I love implementing classes. Make it easy, lazy. That's cool. Glad to hear that, man. So we want to, of course you can get that degree. Of course. Just stay in your classes. That's it. When you stop going to your classes, they stop giving you degrees. As long as you stay in them long enough, eventually they just want to get rid of you. So this is it. So we want to select these. The current model uses logistic regression. The new model uses basically a random forest. And so we had no implementation of a random forest. We had to make one. There was not a fast one, so we had to make one. And that was the goal. The features that you get, a bunch of the features are related to you, like the percentage of all your question views that are in JavaScript, in Vue.js, and Vue component, and parent-child, etc. And then the second thing is about the jobs. If we go look at the jobs have these tags also. We also look at the titles, software developer, remote or home office, things like this. We also look at the job description, and we parse out important pieces of information from the job description and a number of other places throughout, all of what you can find on a job. But basically everything that's here sort of goes into it. And then we decide, okay, what percent likelihood are you to click on this thing or not click on this thing? About to start learning data structures. I am not at a C's get degree mentality. About to start learning data structures and still like recursion pointers passed by value of memory allocation. I still can't believe after one CS course I am way further ahead of you after your first CS course. Yeah, well, I mean, that's life. They get better at teaching this stuff the older you get. So, hooray! Okay, so we have these models. And we need to make it fast. All right, what did we do? We did the simplest conceivable thing at first. Let me go ahead and bring this up. Close this. Oh, every time I get on here, it's like, hey, some new stuff. Updated Visual Studio Code icon again. Gosh, they just keep updating this. It's like a thing. Like, just settle on one. Nobody really cares, do they? What is the ROI on changing an icon? Like, I don't know. That's weird. All right, man. Well, have a good one. Thanks for stopping by. I appreciate it, Ryan. All right. Go to definition improvements. Breadcrumb navigation displayed by default. Smart selection for JavaScript extract. To type alias TypeScript refactoring, integrated terminal supports TrueColor. Oh, that's cool. That's actually good. Better merge conflict display, collapse all command for list and explorers, remote development, preview available and stable. You can now use remote development extensions. I don't know what that is. Whatever, that's cool. All right. So, simplest conceivable thing is you take a decision tree and you basically pull it out into a bunch of nodes like this, and then you just walk through the nodes. Evaluate. You literally just walk through the nodes. You say, give me the first index, and then load up the feature, and then choose which branch to go down. These branches are basically pointers into the nodes. And then you go grab that node like that, And then you just go over and over and over until you get to a leaf. All right, stupid simple, really easy to check whether or not you're actually producing the correct thing. And then the random forest part of it is you just have basically a bunch of trees. Evaluate probability. And then for the trees, it's super, super simple. You just pass in your instances. Nope. Evaluate. Is there an easier one? Yeah, here it is. You just pass in your instance, right? Which is all of your features, all of the stuff you know about the person, plus all of the stuff that you know about the job, all wrapped up into one array of numbers. And then you basically say, for each of the trees, go get the value from that tree, then convert it using the logistic function to tell you, oh wait, no, this isn't correct. There you go. Convert it using the logistic function into a probability, and then return the result. Hooray, Frackberg. But where is the rocket launcher? Oh, we're going to go that route. Yeah, so where is the rocket launcher? Normally, the rocket launchers are pretty basic, man. It's just like an electric switch. All it does is light up a piece of wire. No squirrel. No, it's okay. Yeah, I'm like still decompressing from the amount of work that I have put onto these decision trees for the last 2 weeks. So by all means, feel free to interrupt me. I am not even coding today. All we're doing is like recapping the stuff that we've done, and I'm going to write it down and draw some visualizations so that I don't forget this stuff and probably write a blog post about it. And I think, yeah, I learned an incredible amount on this. A really incredible amount. I think one of the other things that like I'm so happy about on this project is also that I spent an enormous amount of time and energy into it, and I never ran out of ideas, right? Like, nothing took very long to implement. It's decision trees. It's really fast. It's like 8 lines of code, right? Well, I don't know, what, 10 lines of code? That and that. That's it. That's your decision trees. That's all of it. The whole random forest. That's the whole thing. It's just not a hard thing to implement. So you get to iterate really, really quickly, and you get to try a lot of different ideas. And thank you so much, Frackberg. Thank you so much. I really, really, really appreciate that. And it just so happens that this is my first stream this month, so you are in first place. Yeah. Woo! Oh, look, you got a new little thing on there. That's cool. I need to update these icons. Maybe that's what I'll do today. That's a good way to do it. Bits leader. A number 1 is like, what if instead, what should you get for number 1? It's a good question. What kind of icon would be a good representation for my brain theme? I need to flip this around. Left brain, right brain. Left side is analytical. I would say that's more the computery side, and then the right side is more creative, which is more like this brainy looking side. I think that would makes a little more sense. Anyway, what would you get? Maybe brownies. Yeah, because I'm gonna eat a brownie right now. Mm. I like brownies as much as I like rockets. Okay. Um. Yeah, brownies. Maybe it's like brownies and then 'cause brownies are my all-time favorite. Maybe like an ice cream scoop. No. What is something that clearly indicates an order? Nice. I like tacos. I like tacos and brownies. Yeah, like last night I had this idea at like 7:30, but I was laying in bed with my daughter cuz she won't go to sleep unless somebody's like laying in bed with her. And so like half the time she sleeps in our room. And I don't think they work well together either, no. Although there are choco tacos, and that's like effectively a taco and a brownie together, although with a little bit of ice cream. So choco tacos. Have you ever had choco tacos? They're really good. Choco tacos. That's the one. Give me an image. See? Choco tacos. You could put a brownie in there. Okay, that's all ice cream, but you could definitely put a brownie in there, and I think it would still be okay. It's like a waffle cone surround. Mmm. This is a new idea. Choco Browno taco. Nope. Nope. Choco taco is the best name. They usually have nuts in them. I can't eat those. Oh, I'm sorry. Did not realize. Um, let's see. Clearly indicates an order. Oh, well, so no, I had this idea last night. The idea is I was chilling, like in bed with my daughter, and she's like rolling around, and I had this idea. And as soon as she went to sleep, I got up and I was like, okay, I gotta go do this right now. And this idea is a lot of fun. So let me just go through and explain this. Basically, you have all these trees, right? You have 1,000 trees. They're not deep. They're only like, I don't know, 5 levels deep or something like that. 5 decisions deep. And your features are really broken into like user features and job features. And this whole time, you know, you have all the job information up front and you don't have the user information. So we've been sitting here like grinding our heads, being like, how can we pre-calculate all the job information into the trees so that we don't have to look at the job information when the user information comes in. We can just look at the user information against all the trees, and then boom, we have our answers, right? And unfortunately, that turns out to be a real heck of a problem, because if you want to pre-calculate all of the trees based on the user data, you now have 1,000 trees for each of your jobs. And that expands to quite a large amount of data, like hundreds of megabytes. And that is way too much to process on a web tier that is also running Stack Overflow. So, like, that's not real. Like, the maximum amount of memory per request that they're going to, like, realistically allow us to allocate on these machines is, like, maybe a couple of megabytes per request. Like, maybe 5 or 6 at the absolute maximum, and even that would be asking a lot. So grinding through like hundreds of megabytes, nah, it's not going to happen. We're not even going to waste our time on that. And so we've just sort of been ignoring the problem, the whole thing. But the idea that I had when I was sitting in bed was, what if when a user comes in, the user features don't really change, only the job features are different, right? We have 100 jobs, so this would expand out to 100 different trees, or to 1,000 copies, no, 1,000 trees once for every job, which is a lot of data. But we only have one user. So when a user comes in, if we reduce all of the trees by pre-calculating all of theirs, well, we only have one set of trees still. And then we only have to run it over the like 200 job features. Like 650 or so of the features are user features, and only about 200 of them are job features. So this will reduce the amount of memory that we need, like, by an enormous amount, and hopefully it'll make things faster. So we tried it last night, and it was a lot faster. Like, it was on par with how fast the other version we have is. The only problem is, like, in the test wasn't aligned very well with how we were doing the how things are going to run in production. This is another thing, is like the test was we had like 5,000 people and 5,000 jobs, and each person was lined up with one job. Like that's what the test set is. And so we calculated, one full thing at a time. But if you think about the way that it works, you only have one user information for all 5,000 jobs. And that's how we should have been running the test. Instead, what happened is we were running the test as if we were seeing a new person 5,000 times and we had to do 5,000 people in that amount of time. But once you realize that the way that it's actually going to run in production is not the way that we're benchmarking it, then all these different ideas start to come about. And so it's fun. Yeah, the process of shrinking the trees turns out to not be a large amount of code, but it was definitely not the easiest code I've ever written. It's this right here. So you need all this crap as input. And then the way that you shrink the tree is these are your new trees these two are basically where you're going to put your new trees. These are the user features that you get to use to eliminate all the branches for them in these. Then you have your indexes into your existing trees and your indexes into your new trees. And then it's basically like if you're at a leaf, then you can just write it out to the tree at the place where you're supposed to write it. And then if you're not at a leaf, then we need to see if this is something we can get rid of. If it's something we can get rid of, then we only need to pull in one side. So basically, we figure out which direction we're going, whether it's a left branch or a right branch, and then we just say, okay, take that left branch and basically shift the whole thing up. Make the root of that one the root of the shrunk tree. And it makes it, you basically get rid of that branch altogether. And then you shift it up, and now instead of you're basically having the size of your tree each time you get rid of a node. In the case that you have a job feature or a feature that is related to jobs, that there are some interaction features like how far away are you from this job? You can't populate that until the time that the user shows up, and it's specific to each of the jobs. So some of these things you can't eliminate outright, and in those cases you need to basically keep both sides of the tree. So you need to keep those branches, and then as you go over it later on, then you'll look through each of those. And that's it. That's the whole thing for reducing the size of the trees. There's a lot of fanciness that went into this around trying to estimate whether or not it was going to be an improvement, how big of an improvement it was going to be. And the way that we did that is you expand all possible paths through the tree, and then you say, before you shrink it and after you shrink it, what's the average number of branches that you might have to go through per tree, weighted by the percent you expect each sample to go through each branch. And it turns out that when you do that weighting, this shrinks the trees enormously. It shrinks the trees, for 5,000 different users over the jobs that made their way into the test set. It shrunk the average branching from 4.3 branches down to 1.8 branches. So it was a huge reduction, completely huge reduction. The longest ones are still the same size, so that was not an improvement. The longest one, you still have to go down 5 decisions, but still, it turned out to be a bit of an improvement. Yeah, it turned out to be a bit of an improvement, overall. It's just, I'm not entirely sure if we're going to go this route because we've already started, integrating one of the other solutions into the project to get the test set up. And I don't know if there's time to swap this out, how easy or hard that would be. Plus, there's, more work to be done on it. This is super quick and dirty using a recursive solution. This would be a whole lot faster if it wasn't recursive. Yeah, there's just a lot of stuff here. There's just a lot of little stuff. Everything's got to get fixed up. The other thing that this does is some of the trees disappear entirely based on the user data alone. For instance, in some cases it turns out that like the trees end up baselining specific features. So like what percentage of C sharp are you of your tag visits are to C sharp, and if it turns out to be above a certain percentage, then like it just says, okay, here's your score for that, and then you don't have to worry about that tree at all. So that tree completely disappears. And I think, this was quite variable, but this thing returns, did we eliminate the tree entirely? That's what this bool is. And if we did, we can then set the baseline for this because we don't need to evaluate this tree at all for any of the jobs. It's just a baseline. And then when we actually go through, we can just add in the baseline. And that's all we have to do. Yeah, it was fun. That was a good idea. It still has some ways to go. Um, all right, so let's see if I'm going to tell a story about this. Let's see. Let's put some requirements down. Let's go with, I'm going to open up another one of these. And we're going to take a look at my blog. All right, this is my blog. And it looks like I need to pull latest, which I can just do straight from here. Pull. Okay, there we go. So now let's go. I use Hexo for this. If anyone's not familiar with Hexo, it's basically, oh, come on. It's just a little blog engine. That's not it. Hexo npm. That's the one right there. All right, yeah. Basically, you can initialize an entire blog, just like this, and then to create new ones, you just say hexo new, and then you just put in the title right away. And this is going to be how we sped up decision tree processing, and it'll just create you a new thing here. And I'm just going to use this to keep notes for now. They stay in draft format. How we sped up. All right, and I think forget how to do that. There's a way to say it's a draft. Hexo draft. New post source drafts. I should probably put it in source underscore drafts. Yep. New folder. And then take this, put it here. Yeah, I do want to move it. That is in fact what I want to do. Okay. And then you can just say hexo server, which will kick it up. And then you can view it locally. This is why I like Hexo. It's super, super fast. I guess they all kind of really do this. Localhost. I'm not beholden to like any of these. Let's see. Nope, it doesn't show up in here. I was really hoping it would show up in here. Drafts. If you don't want your post processed, you can set layout false in front matter. By default, Hexo uses the file name, okay, drafts. Okay, that's fine. Alright, so the appropriate way to do it would have been to use hexo draft instead of hexo new. And I just learned something. Oh, you can add draft. option when running Hexo, or enable the render drafts setting in config.yml to render drafts. Okay. All right. What do we want to write about? I think the first thing we want to note is the requirements. The requirements for the whole project. How about the goal for the whole project? The requirements for the whole project. And okay, getting it up and running. Verifying correctness. And then what did we do after that? Then we got into how can we make it better. All right, the trivial stuff. All right, I think we're gonna go like this. We're gonna go introduction. Getting it up and running. The most naive possible solution. Verifying correctness. All right. Performance tuning. And this is where it actually gets interesting. The trivial stuff. What kind of trivial stuff was there? Do we remember the trivial stuff? That's a great question. Let's take a look at the history. The history is this one. Can y'all see this? I can't zoom in. That is so lame. Let's go to GitHub where I can zoom in. GitHub slash yep, that's the one right there. Make sure we don't do anything dumb. Okay. And then we came in here and we want to look at the commits. Okay, decision tree perf. Decision trees. Decision trees start. Let's check that out. Alright, this was really trivial stuff. Oh yeah, that's right. Parsing in the parsing the provided model files. Yeah, I guess that was the very first thing we had to do. Then what is this one? Let's just merge those up here. Okay. Getting the test up and going, so we're all still on the, this is the verifying correctness part. This was some garbage. Feature index. Alright, this is when it was still a class and it was still ints and doubles. Okay, so the first thing was shrinking the representation. I think we want to be very clear up here. Our goal is not to make a general purpose tool, but make this specific case as fast as possible. That is going to be like an overarching thing that comes up over and over and over again. I think I'm going to have another brownie. Yes, I am. You know you're in trouble when you eat 2-bite brownies in 1 bite. Should not be doing that. Okay. All right. Testing, evaluate. Silly simple how easy it was to evaluate. Testing, 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 yada yada. Okay. Next commit. XG boost. Model correct. Oh, that's right. The very first day, all we did was the... Yeah, that... Okay, yeah, the very first day, all we did was decision trees. It wasn't until day 2 that we actually did the verifying the correctness part of it, where we evaluated probabilities from the random forest. So the random forest wasn't really around until day 2. And again, like, this code is trivial. Like, this code is ridiculous. This is a random forest. Right there. Okay, that is actually a good one right here. So this is using link. And that was a big problem. Get rid of link. That right there was a huge boost. I don't know why it's so slow. I honestly don't know what it is about calling sum that makes this like atrociously slow. I think maybe this delegate right here is being called, and there's like some expensive part of calling this delegate maybe. I don't know. It was atrociously bad doing this way. Just really, really bad. And then this right here, this isn't actually expensive at all. This is not expensive. Okay. I mean, technically you could write this as like a single return line, right? You just take this, you put it in here, and then instead of returning this, you return this with this inside of it, and boom, 1 line. Like, it is so easy to write a random forest. It's like ridiculous. A very naive version, I should be clear. Okay, so then the next day, now we started the performance work. Okay. First thing that we did, we changed this to a struct. And using structs instead of classes for nodes. And then, oh man, come on. Oh yeah, this was another crazy one right here. This was like a noticeable perf bump by literally just pre-indexing the first one instead of calling node 0. I don't remember exactly how much of a perf bump this was, but I know it was enough that it is still in there. And anytime I change it back, it's still busted. Which is funny, because I think I did put it back. Let's go take a look. On this one... Oh, that's right. You have to do that. Nope, it's okay. We're going to come back to it. And that was it. We didn't change a whole lot the first day. Okay. Getting fast access to the first element, to the first node. I think this is so fast. I want to say the reason that this is so fast is that because we changed it to a struct and we made it a property of the tree, like first is now a property of the tree that is a struct, it is actually storing this very, very, very near where this decision tree reference is. It might even be copying this first for every instance of the decision tree. So when we get the pointer to the decision tree, we already have access to the stuff that's very close to it. Whereas this is like a reference that we then have to go find in some other place in memory that requires you to go like look that up. And I think that's where you get the huge bump from. Like if I were to switch this back to a class, I'm not sure that this would still be fast because it would still have to go look up wherever this thing was stored in memory, which is almost certainly in here. But since it's a struct, it's actually copying the value. That's my guess. I am not an expert in these things, but that's my guess. Okay. So that's all we did for the third day. Look at that. We spent a whole day writing code. This is what we came up with as an improvement. A whole day. That was like 2 hours of streaming. Hey, what's up, Michael Jolly? Thanks for stopping by, man. Lurking's totally cool. I'm just going through and basically writing notes for a blog post that I'm going to write about all of this stuff so that I don't forget any of it and I get to share everything that I learned. All right, decision tree perf, the next one. Okay. For this one. Okay, for this day. All right. Now we want to get into. Maybe we even go something like this. 1, 2, 3. The trivial stuff. And then this isn't the trivial stuff. On the decision tree stuff, yeah, that's right. I will definitely send out a link. And if you hear me say anything crazy while you're lurking, feel free to chime in. Did you end up, I saw you tweeted that you might be looking for a new position. Have you gotten any leads on that so far? Just stack more layers. More layers of... Can you be more specific? Oh, great. That's a good position to be in. Yeah, that's awesome, man. I'm glad to hear that. Get this crap out of my pocket. Stack more layers. Statistical learning. Gentlemen, our learner overgeneralizes because the VC dimension of our kernel is too high. Get some experts and minimize the structural risk in a new one. Rework our loss function. Make the next kernel stable, unbiased, and consider using a soft margin. Oh, stack more layers. Ha! Funny. That's funny. I forget what VC dimension is. The number of VC dimension is the number of data points that you can completely shatter with your model. You know, we had a neural network model for this. Funny enough, we tried it out. And when we did the analysis of like positive predictive value, could not get it to beat this random forest, man. Like for some things, random forest is just really, really good. I'm up to my ears in tech tests at the moment. Also haven't written a resume in like 15 to 18 years, so I'm working on that now. James Fight Me in IRL. Thank you so much for the follow, man. I really appreciate that. The graph isn't even linear. Yeah. Our learner overgeneralist. Yeah, okay. VC dimension. I can't remember having ever used VC dimension in like a decision making process ever. Although I think under the hood it is actually important, just not really. Get some experts to minimize the structural risk of a new one. No. Just add more layers. Layers on one axis, layers on another axis. There's probably a third dimension of layers here too. That's funny. Okay. Now the non-trivial stuff. What was the first non? I was just looking at it. What's the first non-trivial thing? The first non-trivial thing was. Oh yeah, the testing, right? Finding out the real slow parts. I can just start writing this right here. I don't even have to put notes. Get some ideas. Do some profiling. Do some crazier profiling. Simple timers. Time per func. Some insane profiling at the time per assembly line. Question: what PWAs unusable on older versions on Android OS? I have no idea what PWAs are, and that's the end of my thing. I don't know very much about Android at all, but maybe somebody else in the chat here can help you out. Oh, progressive web app. Are progressive web apps usable on older versions on Android OS? Almost certainly, I would say probably. As long as Chrome runs fine on those older versions of Android OS, you can make a lightweight enough single page app, progressive web app. You can make a... Yeah, as long as it's lightweight, I think it would be fine. And if you have those devices, you can just test them. There's also a website for this called... Damn, what's it called? I remember it from my days back in Atlanta. Where you can basically take your website and run it on any device through some, like, cloud API that then sends you back an image of what's happening on that device. Like, it renders it and everything, and then it collects what is actually shown and gives you back a GIF of what happens on that device so you can actually see the thing. I can't remember the name of the website to save my life. I know who would know what it is, though, and I will send them an email and might bring it back on here. I might bring it back on here. Visual Studio Profiler. And what was the other one we used? Dot trace. And then some profiling. This was, yes, simple timers. Browser test site. Wow, I remember. Oh, Browser Stack. Yeah. Browser Stack. I think that's it. Is it Browser Stack? Is that even still around? World's leading testing tool. Okay, well, I'm going to guess that's it. Yeah, you can literally run this on like any test or on any device. And I want to say, I don't know if they're using emulators or like how they're doing it. Like if they have a bunch of devices and a data center somewhere. I don't know how they're doing it. Cool. Yeah, good call, Matt. Is Matt. All right, so then we got the profilers. Get some ideas, like where we think it's slow. Verify those ideas. This actually saved us a ton of time. Problems. With all these methods. Because they're all busted. Basically, they just sort of point you in the right direction, but they don't tell you the real problem. They just tell you like, okay, you're stuck on this function is really expensive, or, you know, you have a lot of branches, or you're being stuck on this branch a lot, or you're being stuck on this memory load a lot, or stuff like that. But why you're stuck on those things is never quite so cut and dry. And how to fix it, even less cut and dry. Okay, whoops, I keep going there, and I keep meaning to go here. Okay, so this was us setting up a console app so that we could actually do all of this crap. This was a bug right here because it should have been plus 1 to the e to the minus 6, or it should have been minus 1 to the e to the minus 6 and plus 1 to the e to the minus 6. I screwed that one up. I fixed that one later. Yeah, this was also reducing things down to floats. That was a big bump, but we already covered that. This was setting up a timing. This was the simple timer right here that we tested to see how long it takes to run some number of whatevers. Then, oh wow, I wonder if that is still a problem. That's a good question. I wonder how much of a problem that is. Shit, not what I meant to do. I hate it when I click the wrong button. What am I looking for? 850. Oh, man, I did leave it in here. Gosh. I wonder if that matters. I want to say it's 840. Look at that. I put it over and over and over again in here. What a huge assumption. Oh, definitely don't care about these two. I don't know what the real number is. I want to say it's like 840. Although I guess it doesn't really matter for the test that these are. Okay, this one doesn't really matter. Does this one matter? Nope, this one doesn't matter. This is just running a test. Okay, alright, these don't matter. What's next? Yeah, this is where we shrunk the sizes. This made a huge difference. This is, ints are 4 bytes, doubles are 8 bytes. So this was 4, 12, 16, 20 bytes. And we shrunk it from 20 bytes to 2 bytes, 6 bytes, 7 bytes, 8 bytes. We shrunk it from 20 bytes to 8 bytes. In a cache line, there are 64 bytes. So going from 20 bytes to 8 bytes got us from 3 decision tree nodes in a cache line to 8 decision tree nodes in a cache line. And that made a huge, huge improvement. Like a completely ridiculous improvement. Double the float. This was us doing the expand all paths. So yeah, this was having an idea about what was wrong and then stopping, literally stopping, and deciding to do the profiling. So that one was important. Okay. So that's it for that one. Remove our history. Goodness me. Probably a good idea that I did that. Update to do. Yep. Greedy ordering attempt. Okay, this was... Hey, what's up, Hugo Doll? Today we are just recapping a lot of the stuff that we did and getting ready to write a blog post about this, so I'm just taking some notes. Okay, then we decided let's go ahead and try to reorder the features. So the idea here is we got done with the profiling, and the profiling said that loading the features, no, it said that, oh, this is complicated. Why is this popping up? No, you can just close that. Ah, cool. Saw you had a few commits. Yeah, how did the perf end up playing out? Man, okay. All right. I'm glad you asked that. So that bug did turn out to be a huge problem. What it was doing was basically taking one tree and only ever evaluating one tree and doing it over and over and over and over and over again. And of course, I put my sanity check in there, right? I had like a test to verify the correctness of this method. The only problem is there were 2 methods that did it. The first one took in a single sample. The second one took in all the samples, right? When I was doing the test, I was running the one that took in all the samples. When I was doing the verification of correctness, I was running the one that only took in one sample. It did work for the implementation for one sample, and I just misused a variable letter for the one that takes in all of the samples. And when that bug got fixed, it went from 25 milliseconds to 120 milliseconds. So we were not... It was still an improvement. I do want to point that out. It was still an improvement, but it was still very far from where we need to be. I was not the person that found the bug. I submitted it to, like, me and other people at work are all sort of going different directions on this project. So that we can try as many ideas as possible instead of all like, okay, did you figure it out? Or I have an idea and then, you know, somebody else is supposed to implement it. Me like telling them exactly what I think is easy to lose stuff in translation here. So we have this giant benchmark project that has basically the decision-making process in it. And it runs this benchmark using .bench or whatever the crap it is, you know, benchmark.net or whatever. And when we ran it through there, that one has a sanity check that sanity checks it against the big one, and that's where we found the bug when we ran it against that. And that was like, oh, great. That sucks. The benchmark itself runs, I don't know, like only 5,000 samples, not 10,000 like we need. So it's really for like relative performance to the other things that are in there, not for the overall. But since then, the idea was correct. So the idea that we changed when we did that is instead of taking the sample and running it through all of the trees, we took a single tree and we ran it through all the samples. Because we thought at the time that the trees were the heavyweight thing and that was the problem and yada yada, et cetera, et cetera. It turns out that that was a very fruitful decision. And when other people started trying out the same method, like swapping the direction there, they were seeing like 50% perf improvements on the stuff that they were working on. So, like, overall, the concept was really good. And we made a lot of improvement just on that. But my implementation and the way that I went about it with the compiled trees was not faster, entirely due to a bug. Now, one interesting thing popped out when I was still using the compiled one, but I ran both directions. I ran one sample through all the trees, and I ran one tree through all the samples in both directions. And it turns out that once this bug was fixed, we actually saw a performance improvement on the one sample through all the trees. And we saw a perf hit on one tree for all the samples. And I was like trying to rack my brain around this. Like, what is going on? What possibly could be happening? And I went back and ran all of the like profiling again. Although when you're doing the compiled trees, the profiler is just like, this is garbage and I give up, because there is no like PDB for it. You're like literally code genning and then compiling as part of the runtime. And so it has no idea where the code for any of this stuff is. It has a hard time even giving you like the machine code for it because it can't like compile it down. I mean, it's just a piece of garbage. Like, all it can basically do is tell you, I called this function and it took a long time to run that function. It can't tell you what was actually happening in that function and what was the slow part. And besides, there was 1,000 functions. It was calling 1,000 different functions. So now all of the time is split out over 1,000 different functions, right? And so it was a little troublesome in that regard. What was the next thing that we did to make an improvement past that? So then I said, let's throw out the compiled trees. Let's go back to the idea of running one sample through all the trees, but how can we make that as fast as possible? Yeah, it had absolute. Well, no, the compiler knew what it was all about. The profiler did not. The profiler was like, I don't know how to even figure out like what code this is running. It's just like we called a method at this address, and then it came back and it was like, oh my gosh. Okay, so then I was like, how can we make this faster? Right? We knew at this point, unquestionably, it was cache pressure that was causing the problem because of my bug. So that turned out to be a good thing. How did we know that? Very simple. We only had one tree and we were running it over all of the samples. And we had one tree and we were running it 1,000 times. So we took that one tree, we ran that one tree 1,000 times. We saw that we didn't have to swap out all these trees, and we got a 75% performance improvement. So swapping out all of these trees and finding all of the trees was causing a lot of memory pressure, right? All of the compiled stuff has to be like pushed in and pushed in and pushed in, and it's running tons and tons and tons of these, and they're compiled in random places in memory. They're not all consecutive because they're just like literally individual things. Exactly, right? So we knew unquestionably that this was just pressure on the cache. Like, we have to go through all this memory. We just need to figure out how we can go through all this memory faster. So what I ended up doing next is taking all of the trees and then creating a giant single array for all of the features, right? So take all of the trees, literally all 1,000 of them, and say, you need to take all of your features and you need to cram it into 32 shorts, however big that is, right? Because there's a maximum of 32 decisions to be made. So you have 32 shorts for the feature indexes. Or maybe it's either 32 or 64. I think it's 64 because you got to have -1 for the leaves. So you take them all into 64 shorts, and then you take 64 shorts, 64 shorts, 64 shorts, 64 shorts, 64 shorts, tons and tons and tons of trees all in a very long single array, right? Then you do the same thing for the values. You shove those all into a separate array. Notice that we now have two things. We have two long arrays that represent the entire tree. But to make it even more interesting, there were four values that went into it, right? So if we go take a look, you also have these where to go on the left branch, where to go on the right branch. And I was like, can we get rid of these? And the answer turns out to be yes. The way that you do it is you just say, if it's true, we're always going to go left. If it's false, we're always going to go right. And the way that you do this is you say, basically, your topmost node is at index 0, and then you just calculate where in the array the left branch would be or the right branch would be. Okay? And let's take a look at something. I'm going to switch the view here. And we're going to do a little example, because I was showing people at work how to do this. I'm probably going to have to yell for you to hear me. Okay. Here you go. Put that up here. All right. I don't know how well you can see this, but I'm trying my best. So basically, we have a tree, right? This is, the top node, the root, and then you have the first node, the second node, the third node, the fourth node, the fifth node, the sixth node. If you want to put these all into a linear array, there's two ways that you can go about doing this. The first one is to take the root and put it at the very first element, and then you basically go row-wise, and you start putting them in. So this is 1, 2, 3, 4, 5, 6. The way that it works is whatever decision you make right here, you take this index, multiply it times 2, which is 0, and if you want to go left, you add 1. If you want to go right, you add 2. If you're on 1, you multiply it times 2, so you get 2. If you want to go to the left node, you add 1. If you want to go to the right node, you add 2. And you'll notice that this all makes sense right here, right? The other way that you can organize this is... I can see well enough. Okay, great. The other way that you can organize this is you take, again, the root and you put it up at the top. And then what you do is you take the entire left node, the entire left branch, and you create a mini tree over here out of just that. So we put 1, and then we say if you go left again, you now end up at 3, but if you go right, you end up at 4, right? Then you take the rest of it and you put it after it. The way that you do this is using an in-order traversal, if you're familiar with that concept. The idea is you always take the left branch. Whenever you get to a node where you need to pop back up, or whenever you visit a node, you add it to the tree. And anytime you go back, then you go to the right. So you go here, 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 back to here. We haven't seen this one, so we add this. Back to here, back to here. We haven't seen this one, so we add this. Go left, add this, back to here, add this one. And you end up with something like this. These are the two ways to build a tree in consecutive memory. Okay? This way and this way both eliminate the need for you to have a separate array to keep track of where the next decision to be made is. Right? These two arrays, this is, well, imagine this is all the feature values, and this is all the feature index values. Right, so this is where I go find it in my features, and this is the value that I compare against it. And what we want to do is, now we don't have to have these other two arrays. So we have taken this entire tree, this thing that took 8 bytes per tree, and we have now crammed it into 6 bytes per tree. Even smaller, and even more importantly than that, this camera just won't focus at all. I don't know what's going on today. It's like the light is screwed up. Oh, it's focusing on this. Well, that's stupid. Okay, whatever. Anyway, you get the point. Let me bring this back now. So, there we go. Futzing with my stuff. Um, so the idea now is we have gotten rid of the need for these two things. So we can now cram the whole thing into 6 bytes per node. And even more importantly than that, we have guaranteed the exact number of nodes that are going to be in every tree. Now we have 2 large arrays that contain all of the information for all of the trees. The real win here is that we have now made all of the memory accesses that we're going to do are going to be consecutive, right? We're going to look at the very first tree, which is these 64 bytes. Then we're going to look at the second tree, which is these 64 bytes. Then we're going to look at the third tree, which is these 64 bytes, and so on and so on and so on and so on and so on. But they're all consecutive, which means that the like prefetching that's built into the hardware can be taken advantage of a lot better here. There is still a little bit of trouble because we're skipping occasionally. At the leaf nodes, we only load one of the 2 pages of leaves because there's 32 leaves. They fill up an entire 64. No, is there? There's not 32 leaves. Yeah, there's 16. No, there's 32. Yeah, there's 32 leaves, and they comprise, two cache pages. So we end up skipping one of them for every tree. And that actually causes a problem when it's not consistent. It turns out that of the 2 ways that I showed how to organize the trees, one of them loads more pages, but because the order in which they get loaded is more consistent, it's like another 20% performance boost. So basically, by doing nothing, we're still taking one sample and grinding it over all the trees. We're now at the point where it's like for 5,000, we were down to like, I don't know, 40 milliseconds or something like that. It was enormously faster, and it was getting kind of close to the point where we could decide to do this or to not do this. But the problem was we had another version that was like still like almost twice as fast as this is. I literally, off the top of my head, cannot explain how that one works. But the concept is basically you take one tree and you're going to run it over all the samples, but you do an insane amount of pre-processing on the data so that all of the feature values that are floats disappear. And the way that you do that is you say, go give me all of the times that will compare this feature index to some value, and give me all of those values. And then we create a decision tree for choosing what value we should actually assign it, right? Which is basically like a binary search at this point. And the idea is that you can now take, because we only use these features a maximum of like 120 times, for 120 different decision values. I should be very specific here. So if we compare feature 1 against value 0.1, 0.2, 0.3, and 0.4, then there's only 4 values we ever compare it against. So we really only need 4 bits of information. Well, you need 5 bits because you need to tell whether it's above or below the last one. But that's it. You really only need like 4 or 5 bits of information. And so you go and you can compress any given feature's value into a single byte, because all we have to do is figure out where in the decision tree to make sure that the decision, the less than or greater than, always produces the exact same result. And because of this, you can now take all of those floats and convert them into bytes, and that is ridiculously fast when you get to comparison. And then they spent a lot of time, the guy who did this one spent a lot of time getting the vectorization right. So you're basically doing entire levels of the tree at a time. And I want to say he also set it up so that it takes one tree and it compares it against all 32 jobs at a time. 32 jobs at a time. It's crazy. Like I said, off the top of my head, it's very difficult to explain. But as I was mentioning earlier before you got here, this is the super interesting thing is the method takes a long time to do all of the pre-processing. And unfortunately, some of this pre-processing was hiding some of the time that it would take per request. Because when a user comes in and we see their information for the first time, we have to do all of this pre-processing. And it was expanding to like 100 and some odd megabytes of data that it was operating on, which was way too much. Like we cannot have allocated 100 megabytes for an individual request. This stuff runs on the same servers that are running Stack Overflow, and it would just take them down if we started doing that. Like we would run out of memory on these boxes in like no time. So we can't do that. Or we're attempting other ways of doing that, but for the time being, like the original idea of it is just not really that tenable. So last night, though, I had another idea, which is I've already got all of these trees, like in these giant arrays, and I can take one sample and I can go over them very quickly. The insight is that the benchmark that we had set up was not really that accurate with how it's going to run in production. In production, we're going to see one user, and we're going to run it against 5,000 jobs, right? Or 10,000 jobs, or whatever it is. And in the test setup, in the benchmark, we have 5,000 users running against one job each, right? So this is not super realistic in the way that this thing is actually going to be used. So I threw out the benchmark and I said, what if I just take the very first user's data, and then I assume that I have all of these other 5,000, we're just going to consider those to be jobs. What you can do is you can take the user data and you can rewrite all of the trees, right? So the idea is you basically take a tree and you look at the first node. If the first node makes a decision based off of a user feature, then I can eliminate that node from the tree altogether. So what we do is we set aside enough memory to rewrite all of the trees, and then we shrink them. So it's a great solution for raw performance, but it isn't specific use, but isn't for this specific use case. Yeah, that is absolutely a good way to put it. If all we were doing ever was predicting one user for one other thing, like period, and we didn't have to do large batches of them very quickly, then it's probably pretty close to the fastest you can do it. I think there's still ways to be even better with cache pressure. I'll get around to it. It's still sort of like hokey in my head, but the idea is, if you're familiar with the way that matrix multiplication works, fast matrix multiplication, you have to take advantage of the cache. And the way that you do that is you calculate partial values for each individual segment of the thing over and over and over and over and over and over again, right? So you basically say, I'm going to take the first 8 rows. Sorry, I keep drawing you off. No, it's okay. No, you're good. You're good. All of this stuff makes sense. And again, this whole thing is about me like getting ready to write a blog post, and all of these ideas are going to be in here for the blog post. So this is like getting in and sort of recapping some of the things that we did, and then sort of at this point getting to the big ideas, which are, okay, here's the conceptual way we're going to make this faster. Here's the different approaches we took at it, and et cetera, et cetera. Okay. So we're rewriting the trees. The idea is we set aside enough space for all of the trees, and then we go through each of the trees, and every time we see a user feature, we throw it away, right? It turns out that in a lot of cases, you end up in throwing entire trees away because it's user features all the way down to a leaf. And in those cases, we completely throw away the tree, and we get to store the value from that leaf as basically a baseline, right? what we say is we don't need to evaluate this tree. It is always going to give us the same value. So for all of the samples, I just start with that value. And if I throw away 100 out of my 1,000 trees, I can sum the value of all 100 of those trees together, and that becomes the baseline for each and every one of my jobs. So we have now done two things. We have reduced the overall number of trees, and we've reduced the average depth of the trees significantly. And both of those things together make it way fast, ridiculously fast, only in the case where the user information doesn't change. When the user information changes and you have to rebuild the tree for every single sample that you run, that's super slow. But if you can rebuild all the trees one time, it only takes about 2 milliseconds to rebuild the trees. And then after that, you can run all 1,000 of the job features. You get another win out of this. The total space that all of these trees are taking up is only about 300, like 384 kilobytes, I want to say. Right? Not an incredible amount. So we're like already in a good place. The second win that you get is you no longer have to copy that user information all over the place. You only have to pass in those 200 or so features for the job to each of the trees. And that's it. And so your cache pressure is greatly reduced. Your speed is incredible. And the speed that we got this to last night, like this all is still happening. So like last night we got the speed of this idea for 5,000 jobs and a single user is around like 28 milliseconds. So we're like definitely in the range of a good thing here. There's still some like hurdles to overcome, and it's like really rough code. Still needs to like verify the correctness of, make sure there's not a bug in like what I did again, because the last time I had speed anywhere near this, there was a bug in it again. But we're getting much and much and much closer. But yeah, that's the long and short of what's been happening. And now I'm just trying to write down enough so that I can get a good blog post in here about it all. And that's what I'm going to keep grinding on. But how are you doing, man? I hope everything's good with you. I'm also taking it easy today. I've been really racking myself these last like 3 weeks when working on all this stuff. It's so fun, but like, I mean, I can't even sleep without like having code dreams on this kind of stuff. It's so much fun. Like these are the kinds of projects where I'm just like, I just love being a developer. I just love doing this. I just love this. Like these are the projects. And you don't get to work on these all the time, but whew, when you do, just trying to understand it all. Yeah, so I normally only stream on Wednesdays, Thursdays, and Fridays. I've been trying to stream on Mondays, but I missed the last 2 weeks just because of like scheduling snafus, not being used to it. Um, but yeah, I missed yesterday. I missed yesterday because we were working on this and we're under a lot of time pressure. The test for this starts on, God, what's today? Today is the 6th. The test for this starts on the 17th, so I have to get all of this done basically by next Friday. Whatever we're going to put into production has to be ready to go by next Friday. And then it's going to run for 2 weeks. And one second. And then it's going to run for 2 weeks. And then we're going to know whether or not it was actually, a waste of time. That's how these things go sometimes. um, yeah, it's good. No, everything's good. Everything's really good. And I'm eating brownies, so I'm gonna have another brownie. Oh yeah, absolutely. I learned so much on this. Oh my goodness. Yeah, no, I've learned like I've learned a lot. I've learned a lot. There were just like I think you learn the most when you do something and you have an expectation in your head, and then what happens is like so far from it. And because it's so far from it, you're like, I have to reconcile this. And then that's when you actually get the learning done. It's like if you don't go into things with an expectation, I feel like the learning opportunities are just like a lot less. But it's like when you make a change, like, choosing that different ordering, I was like, oh man, I've done this amazing thing. I've reduced the number of cache pages that we're going to have to hit by like a third. This should make it so much faster. And then it was slower. And it was like, why is that slower? And then I learned all about how hardware prefetching works. And it's like, it's pretty crazy. Like, it's pretty intense the way that it works. And it's super, super interesting. But it's just one of those things where it's like, okay, now that I know that, how can I use that? Like, can I use that to make this faster and better and whatever? And it turns out, like, the overarching goal of all of this, which is, gonna end up being no surprise to anyone, is reduce the amount of data that you have to use as much as possible. Like, that's the end of the story. And once you get there, yeah, you're just in the best possible spot. Period. There are still so many places where, like, we could improve this, like, even more, though. It's just, I don't know. Right? Your cache size is only 32, and again, we do know that this is cache pressure that is causing, like, all the problems. There are ways to optimize for it, right? Each of the jobs, the things that go into like the final part of the algorithm, is about 200 elements long, maybe 220. No, right at 200. I'm going to say right at 200, maybe 205. So it's about 205 elements, and they're 4 bytes each. So that's 800 bytes, right? 800 and, I don't know, 20, less than a kilobyte. That's the point. So any given job is about a kilobyte. You have 5,000 jobs. The trees themselves are quite small. They're only 30, they're what? 6 times 64, whatever that ends up being. Well, I can tell you, it's 6 pages of memory. Oh, wait, no. I'm talking in number of bytes. 6 by 64. 6 times 64 divided by... That is a number of bytes. Yeah, divided by 64. Okay, so these are using 384 bytes apiece, and you have 1,000 of them, so that's 384 kilobytes, and then you have 5,000 jobs at about a kilobyte apiece. So the way to like really optimize this is to balance it out just right, so that you have a bunch of trees in there and a bunch of jobs in there, and then to do all of the work for that group together. Because when you only have one job, and then you try to do all the trees, you end up churning through all of this data over and over and over and over and over again. Whereas if you loaded 8 of these, or 10 of these, and you're using 10 kilobytes over here, and then you load up, I don't know what, a third of the trees, and you do a third of the trees for all of these, you get much more work done in a small amount of cache, and then you can move over. And now you have to move over, a factor of 8 less times, or whatever number, 10 less times, whatever number of jobs you end up choosing, and you can do even better at it. It's like you'd have to set up a math equation to like figure out what the optimal is, but I would imagine that if you did that and then you plugged it in, you'd be pretty close to what the real speed's going to end up being. Anyway, come around to that. Okay, let's write a few more lines because it's 1:49. I've been on here for 2 hours having a. This is a bunch of fun though. Like I said, I'm taking it easy today. Okay, so the next thing that we did was the greedy reordering. Okay. So now let's talk about concepts. Not concepts, that's the wrong word here. Generalized problems. Is that it? Is that the way to say it? Approaches. Okay. The overall problem. Cash pressure. How did we decide it was cash pressure? The bug that pretty clearly identified it as cash pressure. Hey, Kuro Hayo, thank you so much for the follow. I really appreciate that. After the last weeks of churning and brain grinding on this, you deserve to take it easy. Yeah, I mean, I've been unfortunately eating way too many brownies. I need to put the lid back on that here, so I don't like get sick. Probably get another coffee. Oh. One second. Okay. The overall problem, let's see. We determined that it's cash pressure. Okay. Ideas to fix it. Approaches. General approaches to fixing it. Reduce the memory size. Hey, we already did that once. What are the other things? Reduce the working set size. And access data in predictable patterns. I don't want to really get into it like this. I want this to sort of come later on. No, I want that right there. Okay. Decision tree. All right, remember, we're just trying to solve our specific use case, not general purpose trees. Sounded like the part of it was not worrying about the number of pages as much as the layout. Yes and no. Here, let's draw it like this. Should be able to draw this pretty quickly. Let's go like boom. There we go. Let's make this bigger. Okay. So let's say you have each one of these is memory. And keep in mind that like on the actual like hardware itself, each of these things. Okay, so here we go. All right, you kind of get the point. This is the memory. And then what we have is, let's take, oops, need that to be black. Need that to be black, not blue. I need it to be black. And then I need to escape, and then I need to go to red. All right. Imagine inside of each of these boxes is another line of memory. Over and over and over and over and over again. In fact, let's add it in like this. Let's make it a little bit bigger. What? Didn't I copy and paste it? Oh, I see. I copied and pasted the whole thing. Well, that's silly. That's not actually what I wanted to do. Damn it. Okay, I give up. We're just going to draw it by hand. You're just going to have to like bear with me on this. So basically, imagine inside of each of these blocks, there's actually a bunch of different rows of memory. Okay? And to be very specific, let's say there is like 8. Okay? And you're not going to actually see 8 here because I'm not going to be able to cram it in. But I'm trying my hardest. So in each of these, there is a bunch of these rows of data, right? Inside, let's say this is one cache line right here. And then this is a second cache line, and then this is a third cache line, and this is a fourth cache line, a fifth cache line, sixth cache line, etc. Right? The idea is that if you only load this, and you want to do a matrix multiplication, you can load this cache line, this cache line, and this cache line, and this cache line, and this cache line, and this cache line in very rapid fashion. Very, very quickly. No problems whatsoever. But to do the matrix multiplication, the next one you load is actually going to look like this. Right? You need to do this top red one by this green one. Okay? When you load a cache line, you have to load cache lines in a horizontal fashion. You don't have a choice. So when you load a cache line, you have to load that cache line or that cache line, right? There is no cache line that goes this direction. It just doesn't exist. So what happens is if you just need these 8 values over here that are on this first one over here that are vertical, you have to load all 8 of these cache lines right here in order to pull out the first element of each of the cache lines. And that's really bad. So you have to load for this one row that is, let's call it, I don't know, what, 1,000 elements across, that you can load super, super, super fast. You now have to load this cache line, all 1,000 of the cache lines this way to pull out 1,000 of the values. So you have to load 16,000 values in order to get your 1,000 values out, right? That's a shitload of work that you don't need to do. Because instead, what you can do is you can just load this cache line, right here, and then you can load this one right here, and then you can load this one right here, and all of these cache lines, like this, right? You can load all of the cache lines in this one block, and then you can do all of the operations that you need to do without ever having to go and load cache lines that contain data that you don't need, right? We can do all of the work for this one block, but if we wanted to do this second row right here, and then we wanted to multiply it times this second row of cache right here, we're at the exact same problem, right? To load this row, super fast. To load this column, again, I now have to go and reload each one of these lines, each one of these thousands of lines. Okay? And so the point is we're trying to find a way to balance the number of trees and the number of jobs so that we load the fewest number of cache lines at a time. And we do as much work as we can on just the stuff that's in the working set, that's in the cache, because we can grind through that super, super fast. And then we can go load everything in this cache block, right? And we can go do all the work in this cache block. And then we can go do all the work in the next cache block. And by doing each one of these this way, you can cut out, orders of magnitude amount of work that is actually, like, it doesn't seem like additional work from like an algorithmic perspective. The work is in how long you have to wait, the latency for the data to be available for you to do the work. And you can reduce that by orders of magnitude. So you're still doing like n-cubed operations to do your to do your, help me out, matrix multiplication. But, these cache lines will load one after another because of the way that the hardware like prefetching works. But these don't get preloaded like that. These don't get preloaded. You have to load this entire 8 values to grab out one value, and you have to do that 1,000 times. Right. Instead, if we just load these 8 cache lines that are in here, we can do a very large portion of the computation for the cost of loading 8 memory accesses, period. And because of the striding of these, you can load these efficiently. But even without the the prefetching, you can still gain a lot by not having to load these 1,000 things 8 times. Instead, you just load these 1,000 things 1 time. And that's it. That's the whole point of like cache pressure and trying to make use of the things that are in there by putting them in the right places. I hope that makes sense. I'm going to save this as stream graphics. Stream graphics. Look, another matrix multiplication. I'm not going to put it in matrix multiplication. I'm going to put it in fast. And this one is called a JPEG? No. A PNG? Yeah. Let's go with cache pressure example. I think I got it, but may come back around for replay later to make sure I got. Yeah, I need to get better at like explaining this. I would love to like come up with a way to like put the math to it to show that like by loading one row at a time and loading the entire row, like we're doing, in order to do this one cache line of multiplications, we have to load these other 7 anyway. And then instead of doing these other verticals, since they're already in memory, instead we have decided to throw those away and start loading up this next block just to multiply it against this one top one, right? And then we throw those away to do this next one. And then we throw these away to do these next ones. And then we come back and we're like, okay, let's do the second row. We haven't even gone over here yet. And that's where you start to get into the loading over and over and over and over and over again. And this trick is called striding. It's a pretty common pattern, but it makes your code really ugly. I mean, like atrociously ugly to read, like almost impossible to understand unless you like absolutely know what's going on and why it is that way. Like we showed earlier that the basic random forest is like 8 lines of code, right? It's just not a lot of code. And then once you want to start making it a little bit faster, it gets a little more complicated and then a little more complicated and then a little more complicated, and eventually it just like completely goes out of control. Okay. That was that. Damn, that's not what I wanted. Let's see here. What else did we do? Oh yeah, feature reordering. Okay. All right, so this is going to be reorder the features. Idea is that the features jump all over the place. If we put commonly access features close to each other, it should greatly reduce the number of cache pages that we need. Yeah. Took the greedy approach. Describe the evaluation function. Man, this is going to be like a whole series of blog posts, what it feels like. Each one for an approach, maybe. I don't know. I don't want it to be like a book where you sit down and you can't read it. Like, I much prefer being able to like read something in 5 minutes and get a general understanding of it. All right, second approach. We tried to reorder the features. What did we do after that? That was the greedy thing. That's where we actually implemented all of that. Greedy feature reordering again. Oh yeah, here were our predictions. Oh, funny enough. Okay, so it started off at 4.3. What do you think it actually got down to? So you originally said it was going to get down to like 3.775. I said it was going to get down to 3.85. Keeping in mind the idea here is that this was the average number of decisions you had to make in order to reach a leaf per tree. Yeah, it did. It got down to around like 2.5. Yeah, that's right. Okay, I did say that. Yeah, I was really blown away by that, by the way. I was just like completely out of my mind how it managed to do that. It still turned out not to be, a huge improvement. It was a little bit of improvement, but it wasn't a huge improvement. It started off, this is what it started off at, 4.35. Yeah, and this was another one of those times where I was like, I totally expected that if we reduced the pages by almost half, Like we had reduced the number of page hits by almost half, that it was going to greatly improve it. And that was not true. It turned out that was not true. I mean, it was still a noticeable, like, a few milliseconds over the course of 10,000 trees, 10,000 jobs, but it was just one of those things where it was like, I was expecting it to be like half the time or 40% of the time. I think you're right. A series of short articles with these sections. What we wanted to do, the approach, explanation, implementation, what really happened, why did it work or not work. Yeah. I think I'm going to spend time on each approach. Like the beginning is probably going to like include all of this trivial stuff and be like, "Hey, here's all the like I bet you would have tried this kind of stuff." Like, and then let's get into the and then let's get into to this. All right, remember the problem. Let's refocus. And then kind of grinding into it like, yeah, one little bit at a time, going over one approach. And maybe just queue up like one of these a day for a week or something. All right, the next approach that we tried, we did the reordering, and man, I was so bummed about this. We put so much effort into this, first off, and then it didn't do anything, like at all. And it was just really frustrating. Kind of what it came down to. Okay. Anyway, next one. Do the work, all jobs, one tree at a time. Okay. Evaluate all jobs, all samples for one tree at a time. Okay. There were 2 places we loaded from memory. One was features, other was jobs. So this is the next likely approach. Also, what was the other thing that what was the other way that this, what was the other thing that happened to do this? To parallel comparing, sorting, searching algorithms, introduce it, explain it, show it. Why would it work? Would it not work for this scenario? To parallel teaching it in an academic setting. That's a really good idea. I'll take note of that here. The Hugo doll. I'll keep that in there for now. And then that's the feature reordering. This was testing the time on the feature reordering. Setting up the test. Right? Okay, this is where we switched over the thing to do one tree all at a time. Where was the magic in this? I want to say it was in XGBoost. There it is. Okay, here is the bug, right? So this is the trees, and then this is the instances. And the trees I indexed by I, as I was supposed to, and the instances I indexed by I, which I was not supposed to, right? And so what was happening is it was basically taking the same tree and evaluating it against the same instance 1,000 times. Well, 10,000 times, right? And this is not swapping out memory, and that's how we know that cache pressure is the problem, because this resulted in a huge improvement in time, but did not actually do the work it was supposed to do. I told you that there were two of these. There is a second version of this which just takes in a single instance, and the single instance one obviously does it correctly because it only loops over the trees and didn't have to loop over the instances. So that was just a bug, but it turned out to be quite the useful bug. But the interesting thing is, like, order-wise, we didn't find this out. We didn't verify this. We don't know this till later. After we screwed up an approach. Luckily, it happened to be one of the first approaches, so maybe I can move this. Actually, I am. I'm just going to move this. Guess what? It's way faster. Guess what? It's also got a huge bug. The bug I clearly identified it as cache pressure, though, which really narrowed down the future ideas. Okay. That was a good one. Yeah, that was a really good one. Okay. That's all we did on that day. Then we said, okay, now we were like, okay, we have these trees. Let's do compiled trees. Oh, man. Lesson learned. Every win might not be right. Even when we're way wrong, we find out something extremely useful. That is so true. Absolutely. Alright, compiled trees. The tree compilation was a fun one. I'm doing Markdown wrong. These go back to the beginning. Wow. What a waste of time. I feel kind of dumb about that. Ah. I cannot type today. Okay, I did mark down right up here. I just screwed it up down here. Okay. Compiled trees. There is always an extra branch at the end. Can we eliminate the extra branch? That's how that one came up. Let's code gen a function for each tree to reduce it as much as possible, and coincidentally to pop out the number of which columns. Okay, this was insanely fast. Actually, I didn't recognize this bug until after this. Because it was after we did this. Alright, it was after we did this where I sent it over and was like, "Can I get this code reviewed? Blah blah blah. Let's get this whatever." And that's where the bug was found. So now we know that these past two approaches. Wait, what was the also? All right, there were two places we loaded from memory. One was features, other was jobs. So this was the most likely approach. Also, the trees are quite heavy, and churning through all that data is expensive. So we should reduce the churn. Okay, perfect. We were all feeling pretty good up to this point. Okay, compiled trees. Alright, once the compiled trees failed, the idea was approach. Better memory alignment for the trees. Okay. The trees were stored in objects. The trees were stored in objects that were spread out in memory. What if we put them all close together? Can we also get rid of the indexes for the branches? Because that would eliminate some lookups. And shrink the size even more. This was an actual win. Like a 50% win. That was a big one. Alright, what else? What else? Then you know what? I think that's actually going to be it for today. Let's see, where are we? More stuff, including sigil, was pushing to the stack in the reverse order. Okay, this is when I actually got that done. Is this where we fixed the bug? No. Nope. Bug was still here on that one. Oh, that's how I actually got there. The tree compilation was the thing that put all of the trees into a single array as functions, as an array of functions. Oh yeah, that's why that one got faster. And then I was like, oh, what if we do the same thing? Okay, yeah, all right. That actually makes more sense now. And then that was silly. I tried to run it on Windows, and Windows added line endings. And then I think this is what I did. Oh, there, I fixed that bug. This is where we did the flat. Did I not check in what I have? What's going on? Oh, I didn't. Look at that. I didn't check it in. Okay. Tree shrink. Let's push that up. Oh, I fixed it in a different branch. Oh, that makes sense, actually. Oh, yeah, the production. Oh, there it is. Major bug. Yeah. Okay. So this is try. Refresh? Yeah, tree shrink. There we go. All of this. I should merge this in. All of this work actually made its way in the real project. Okay. Then we tried tree shrinking. Okay, then we tried pre-computing. All right, let's go back to here. Approach. Pre-compute as much as possible. This is something we had been thinking about all along, but we tried repeatedly to pre-compute the jobs, only because these are branches, you now have to create trees for each job, create a set of trees for each job, which is an asinine. I'm gonna go with inines. Asinine amount of memory usage, which is beyond our allowance. Instead, let's oh yeah, that was another thing. Right. This was it. Look at the problem holistically. Take a step back and look at the whole problem. Not just optimize the thing the profiler said was slow. But focus on the whole problem. And then same thing here. Instead, let's take a step back, take another. Hell, this is going to be my blog post. It's just going to be Markdown. Almost tells a story. Just be like, read along, watch the video. Instead, let's take another step back and look at the whole test compared to what's going to happen in production. We can't, there's only one user, so we can pre-compute the user, then run it for all jobs. Okay. All right, and that is going to be it. I'm going to save this off. Tomorrow I'm going to be in late. My son is in art camp, and it's the last day of art camp, and they have this like thing where they're going to show us whatever it is that they've been working on all week. So I'm going to be at that, and then I'm probably going to go out to lunch. So I probably won't be on until about 2 o'clock tomorrow, and then I'll hang out until 4. So if you want to stop by, I'd really appreciate it. That'd be awesome. If you don't, whatever, that's cool too. And, thanks everybody for hanging out. I know this was not like a coding thing. I hope it was informative. I hope you enjoyed it. And I will see y'all tomorrow. I am going to look for somebody to raid. If you have anybody you'd like to choose, Now would be a good time. I will have fun at art camp. He's been having a blast. Like, he either really gets into things or he just doesn't get into them at all, and he has been really getting into this one. Let's see. Let's go with let's go with I think Raimu. I think Raimu. There we go. Yay. All right, again. Instafluff, the Michael Jolly, yeah. I really want to spread it out a little bit. Thanks a lot, Hugo. You have a good day as well, man. I really enjoyed it today, and hopefully I'll see you tomorrow. If not, have a good weekend. All right, we're gonna go raid now.